Now you started? Okay. Heavenly Father, we thank you for this day. Again, Lord, I just pray you'd bless our work and guide our thoughts today, Lord. In your name I pray. Amen. Let's see here. So let me work a somewhat relevant problem for you guys. Example 1. What if we're solving, say, y prime prime, and I'll do something a little bit different. 9y prime equals to the cosine of 3t minus the sine of 3t. And I'll put an 8 here just for kicks. So the problem with this kind of problem is what? What's the homogeneous solution here? So why? This is because y, or as my brother Andrew used to say, cos by. Trademark pending. Let's see here. Lambda squared plus 9 equals to 0 gave us lambda equals to plus or minus 3i. And from that, of course, I get this homogeneous solution. Of course, the trouble with that, then, is that that homogeneous solution looks just like our forcing function, right? So the method of annihilators will basically tell us that we should make yp equal to t times a cosine 3t plus b sine 3t. All right. And of course, I'm happy if you use method of annihilators, but if you didn't, and you just wrote this down, well, great. All right. For your quiz that you guys were just working on, there's no 3, right? It's just t, because it's just y prime prime plus y. Oh, I'm sorry. Okay. You're not allowed to do that. Just saying. And then we have to differentiate. And so, you know, because we're going to plug it in, so there is a product rule here. In fact, 2 of them. Let's see here. So this gives me minus 3a sine 3t plus 3b cosine 3t, right? I personally find it's helpful to regroup things in terms of cosine and sine at this point. So like, I'm going to collect all my cosine 3t terms. I've got an a minus 3at. I'm sorry, cosine 3 what? Plus 3bt, right? Sines. Sine 3t, how many of those do I got? I got a b and minus 3at. The reason I do that, just to, and I'm sorry guys, you got to watch me here. Is this y prime prime? No, I'm just reorganizing y prime. I'm just cleaning up y prime at the moment. Now y prime prime. All right, so that's going to give me minus, don't forget your chain rule, minus 3 sine 3t, this stuff, plus 3b cosine 3t. I just did the product rule on the first term. Then I did the product rule on the second term. So now I will organize things again. What do I got? Yp prime prime equal to, so I'll collect things together. I've got a cosine 3t, right? And what do I have? I've got this 3b, right? But I've got another 3b from here. So in total, I have 6b. How many t's do I have with the cosine 3t terms? You see that? Minus 9a, right? Agree? So I collect together all my cosine t terms, 3t terms. Now my sine 3t terms, what I got there, sine 3t. Let's see here. I've got, I think, minus 6a, and I believe minus 9bt. See, because this minus 3 times this minus 3b gives me minus 9bt. So there are various ways to organize this calculation. One way we could organize it would just be to notice that this expression is really what? This is really, 6b cosine 3t, right? Minus 6a sine 3t minus 9 times what? What's left? What does this piece and this piece together give me? I factor out the 9 and the minus. I got one of these guys, right? So that's really minus 9yp. So we have this equation that yp prime prime equals to that. And so you can easily see that that says that yp prime prime plus 9yp is equal to 6b cosine 3t minus 6a sine 3t. Make sense? Alternatively, you could plug it back into the differential equation and watch stuff cancel. It's up to you. It's not really much different what I'm saying than what I just said. Now what's that equal to? The forcing term, right, which is 8 cosine 3t minus sine 3t. So from this, I can get what? Equate coefficients, right? So the cosine has to match the cosine, and the sine coefficient has to match the sine coefficient. So from that, I get 6b equals to 8, and minus 6a equals to minus 1. So therefore, b is equal to 8/6, otherwise known as 4/3. And a is 1/6. And in total, in summary, or conclusion, whatever you like, we have y is equal to c1 cosine 3t plus c2 sine 3t plus 1/6 t cosine 3t plus, funny, 4/3 t sine 3t. And there you go. Your problem 2 on the quiz was very much like this. A little bit easier, right? Because I didn't stick you with the 3s chain ruling everywhere. Yeah. Any questions? So, yeah? Oh, yeah, I'm sorry about that. That was poor planning on my part. I should have given you guys more space for that one. I usually do. What I should have done is just move that up a little bit. Well, the first problem actually took the whole space, too. I don't know. Yeah. Sorry about that. I usually, as you know, when we have a test, I give you guys just one side, and you have the back side to work on. So there's that. But, yeah, sorry about that. So we should talk about physics a little bit, right? What's this an example of? Like, what's going on here? How to understand this math we just did? What happens here as t goes to infinity? If you look at the absolute value of y, what's it going to as t goes to infinity? And how can we understand that in terms of energy? What's that? Oh. Am I going to have to separate you guys? I'm joking. They're fine. This is what? Look, you've got t, and t times cosine t, what's that do? It just, and larger and larger and larger. I mean, this goes to infinity. I took absolute value here just to be unambiguous. But as you can see, I mean, what's actually going to happen? This would be something like, if you're looking at, ma equal to the spring force, right? So minus kx, right? So we got what? We got m y prime prime plus ky, and there's It's not quite that though, right? There's also plus what? And I probably shouldn't use x there. Minus ky plus an external force, right? The external force for us is this thing, right? The external force on the spring mass problem. So, you know, that's... now here the mass is 1, right? And the spring constant k apparently is 9 for our problem. So what's the so-called natural frequency? So this gives omega equals to the square root of k over m, right? That's the square root of 9 in this case, which is 3. So 3 radians per second is the natural frequency for this system, right? And we're putting an external force, which is also at 3 radians per second, right? So what happens is you just keep feeding energy into the system, and it doesn't go away, right? There's no friction force here to damp the energy out, and it just keeps adding energy and energy and energy, and so the motion grows unbounded. This is what's known as pure resonance, right? So you probably have seen the picture of the Tacoma Narrow Bridge. You guys, the bridge is wobbly, and so there it's something a little bit more complicated, something like the wind, and people will debate, of course, but one popular explanation which has been given over the years is like the wind happens to blow over the bridge in such a way that it hits the natural frequency and just keeps building this side-to-side motion until finally the bridge breaks. And I'm sad to say, I think a dog died. I forget, but yeah. If it was a cat, I mean, we'd be okay, but anyway, that dog would have long since died anyway, but it's an old story. But this is pure resonance, right? And but real physical systems, what do they look like? You know. So I guess we should talk about a few different things here today. One thing we should talk about is if you have m, if you have m y prime prime plus k y prime plus oh, I'm sorry, not k, beta, maybe b y prime plus ky equal to external force. Ignoring the external force, you can look at this. There are 3 cases, right? You've got overdamped, right? You've got critically damped. And what's the other case? Underdamped, or sometimes called weakly damped. And so these are just different cases. I mean, in terms of, so here we have both of the eigenvalues, the characteristic values for the characteristic equation. Lambda 1, lambda 2 are both distinct real. Critically damped is when lambda 1 equals to lambda 2, right? And underdamped is when lambda is complex. Those are the 3 cases that are possible for a second order constant coefficient difference. I mean, okay, so in here, kind of, here you have different cases. I mean, maybe there's a 4th case. I mean, I don't know. I guess maybe a 4th case is pure harmonic or simple harmonic motion, right? This would be the case that lambda is pure imaginary. I don't know. I guess people might. I don't really care about the classification scheme here so much. The point is you should be aware of this. Of course, pure imaginary is when we get simple harmonic motion. That comes from not having a friction force at all, right? Every single last one of these, for real physical problems, what do we have? We have m is positive, right? Mass is positive. I think we can all agree. The friction, B, is what? It's greater than or equal to 0, right? And the spring constant K, for real physical springs, is positive as well. I guess it could be equal to 0. You could have the case that you're not really having a spring, right? I mean, maybe, I guess for spring mass problems, I probably should just, I don't know. I mean, it's not a debate I want to get into. So for these conditions on m, b, and k, what can we say about the nature of these solutions? So what do we? Let's just look at it. We've got m lambda squared, right, plus b lambda plus k equals to 0. This is the characteristic equation. And what happens when we complete the square on this thing? So I'll divide by m. Divide by m. And then you can see that this says that, just getting straight to the point, lambda is equal to, what is it? Minus b plus or minus the square root of what? B divided by m squared minus 4 times 1 times k over m. What am I doing? Yeah, quadratic formula, right? If you don't like this, complete the square. Great. And we could clean this up a bit, right? If I multiply, I mean, I've got a, yeah, why don't I multiply this whole thing by, I don't know. I kind of want to clean this formula up. I'm not sure how I want to do it yet. I have trouble making decisions, you know. Let's see here. Plus or minus the square root of, let's say 1 over m squared is a nice thing to pull out here, yeah? If I do that, I've got what? B squared minus what? 4. I factored out m squared, so 4km, right? So let's see here. What's that give me? Minus, I can pull the m out. But if I do, I want an m over here too, right? So let me rewrite this as bm over m. So it looks like I got minus mb plus or minus the square root of m. Sorry, I wanted to get this over with here. Bring the m downstairs. So b squared minus 4km. Sorry, my handwriting's deteriorating as we go down the board here. 2m. All right, finally. Go back over here. So what I've just derived is that lambda is equal to minus bm plus or minus the square root of, what was it? B squared minus 4km divided by 2m, it looks like. So you can tell which case you're in by just looking at the discriminant, right? So this is the discriminant. So to get overdamped, we would be looking at b squared minus 4km greater than 0, right? Critically damped would be when b squared minus 4km is equal to 0, right? And underdamped would be when b squared minus 4km is less than 0, right? Let's talk about the underdamped case a little bit more. So underdamped, we have b squared minus 4km is less than 0, right? So what's my lambda equal to? I'm going to rewrite it. It's minus b over 2m. It's rather minus b over 2, all right? Plus or minus I times the square root of 4km minus b squared. So what I did was I factored a minus out of the discriminant and pulled out a plus or minus I, right? I mean, changed it to plus or minus I. Notice the I, yeah? So, you know, this is giving us solutions, basically. What solutions look like? Y equals to some constant, a, e to the minus b over 2t, and then something like sine of the square root of 4km minus b squared t plus some phase angle. Or you could write c1 exponential cosine plus c2 exponential sine. But I combined the cosine and sine into a single sinusoid with a shifted phase.
Where did your denominator go? The 2m?
Oh, right. I knew something felt wrong here. It's still in the marker, apparently. So, yes, 2m, thank you. Thank you. That's not optional. Yes, I'm so sorry. And that's actually important because if we look at omega equal to the square root of, thank you, that was about to confuse me very much in our next calculation here. So I'd like to actually simplify this if I can to try to understand things a little bit more, right? Can we simplify that? We can simplify that, right? We can kind of undo, and put the m back inside again, right, basically. So this is the square root of 4km minus b squared over what? Over 4m squared, right? M is positive. I can pass it in and out of the square root as long as I take care to square it. Spare a square? Yes, I can spare a square. Let's see here. Square root of, sorry, it's awful. K over m, right? Minus b squared over 4m squared. And there you go. This is the formula for the natural quasi-frequency in underdamped case. Why do I say quasi-frequency? What's that? It's not harmonic, right? It's not really a periodic function, right? Technically speaking, we should really only talk about frequencies for functions that repeat with some period. This is not actually a periodic function because it never gets back to where it started, right? This exponential gives it some kind of, there's an envelope. Hey, let me show you instead. If my battery isn't dead. I really need to get a new battery for this thing. So, while I'm getting this computer to behave, can you guys tell me what's the one thing that's common to all of these different solutions? Look at the I mean, it's totally physically natural, but if you look at this formula, look at the real part before the square root, right? You've got this, where's my best formula? This, if you look at it, certainly in this case, certainly in the underdamped case, the real part of the complex solution is negative, right? Which means you're always having an exponential with a negative argument, which means that goes to 0, right? So yeah, I get sines and cosines, but they're damped, unless we're in the case 4 pure harmonic motion, in which case the motion's still bounded, but it just keeps oscillating, right? But certainly in the underdamped case, the solutions go to 0. How about the critically damped case? When you have 4km equal to 0, your eigenvalues, characteristics, my eigenvalues keep showing, sorry about that. Characteristic values, just this, so it's minus b over 2. Again, negative exponent, right? You guys remember L'Hopital's rule basically tells us t times an exponential still dies if the exponential's got a negative argument. So still, time goes to infinity, goes to 0, right? And then in the overdamped case, we've got distinct real roots. And it's pretty easy to see that b in magnitude beats b squared minus some positive quantity, right? So clearly, both the minus minus and the minus plus, they're both in total negative quantities. So these lambda 1 and lambda 2 have to be negative roots for real physical problems. In every single case, the homogeneous solution either goes to 0 or it's bounded. It's bounded in the case we have no resistance, but otherwise, friction makes the homogeneous solution go to 0. For this reason, we call the homogeneous solution the transient solution, because it just exists for a short time and then, either resistance for an RLC circuit, or in this case, the friction force kills the energy and makes that piece of the solution die to 0. Now, the particular solution, on the other hand, doesn't suffer this fate, right? The particular solution is from an external force, which if it goes on and on, there's no reason that the particular solution doesn't go on and on. So sometimes in engineering, you guys will call the particular solution the so-called steady state solution, right? Because it's the piece which exists for a long time. if I can find my, I made you guys a couple pictures here. If I can, oh, yeah, duh. Can you, Mr. Excellent, can you hit the lights for me? Thanks. Yeah, that's cool. I'll send you guys, well, maybe I won't send you a link. I don't know if it really matters. Look here. So you guys know what sines and cosines look like, right? If you change the natural frequency, you can make it be more, you compress the frequency or, I mean, there it is. That's the pure harmonic motion. Of course, you guys know about that already. Here is what's this? This is weakly damped, right? So you see there's kind of like this exponential. Let me zoom in here and focus on positive time. So what happens, see that W is the sort of the quasi-frequency, right? So if I've got a negative quasi-frequency, which is weird, make it a positive quasi, there we go. As the quasi-frequency increases, of course, it gets more wiggly, but it's always stuck between that, exponential. Now I can make the exponential be more severe, right? And then it'll kill it off faster. And then here is an unphysical solution. See, that's would be a positive exponential. This is not a solution you'd find from a spring mass problem, right? It's like I hit the spring and I just gave it a tap and it just kept getting wider and wider for like the friction force just made the spring break. It's crazy. That doesn't happen. Maybe that could be an episode of Fringe or something, right? But and then here is the this is critically damped. It occurs to me I failed to have overdamped in my plot. Sorry about that. I'll fix it in just a second here. So here we're looking at overdamped. Let me adjust my B. That's how much of the exponential piece I'm adding. So let me just add one of them for the sake of discussion. Here's plus one exponential piece. And then the A is the B minus B over 2A, right? So if I make that bigger, it dies to zero faster. And here's an unphysical solution. Okay. No, there's an unphysical solution. This one's still physical. It's just, I should zoom out a bit. You see it gets to zero. Now, all right. Finally, one more. Y equals to, let's say, e to the ax plus e to the, I don't know, I'll do bx. And I really should put some sliders in here. What did I have? W? I'll use W for something else. And Q. All right, so to make this physical, I should have A and B both negative, right? Here's a couple negative, and I probably should turn off the other solution just to not confuse us. There we go. So this is an overdamped case, for example. Now if I can go up here and I can adjust the, how much the first solution we're getting, it looks like that, right? Depending on how much of the first one I get, it looks like that. Or I can adjust how much of the second one I'm getting, like this, So these are the kinds of response curves which are possible in the overdamped case, right? As you can see, they all lead to the same point, which is what? Eventually they go to zero. But how they go to zero is different for different initial conditions, right? So this is what we've been solving in the second order case. These are all the possibilities, what they look like. So what's the one case you don't want for if we're talking about, springs on a car, obviously this is what you don't want, right? Like, you don't want to go over a bump and then experience this kind of motion, right? Like, this is not optimal shock absorbing, right? You'd rather be in the critically or overdamped case, because then you hit the thing, the car does what it needs to, and then it's back to zero again, right? You want that kind of response. So in my notes, guys, oops. Come on. Come on. I have, these cases are in like pages 93 to, 95. Here I have the dictionary between the RLC circuit and what we're looking at, right? This is the, Kirchhoff's voltage law gives you this, well, maybe physics gives you this equation anyway. And you can compare it, of course, to the spring mass problem, and you can see there's a dictionary. Mass is like inductance, resistance is like the friction coefficient, and the reciprocal of capacitance is in some way analogous to the spring constant. And so any formula we've derived for spring mass problem, there's a corresponding formula for the RLC circuit problem, right? So that's kind of neat. All right, what I was supposed to talk to you, though, about, I see I have given you too much time for the quiz, so I'm going to have to do a little projecting here. You'll forgive me, hopefully. So you've seen, come on. Sorry, I'm trying to find the right zoom factor here. So we saw in the quiz pure resonance, right? But there's an interesting subsidiary question, which is, so suppose you don't have a simple harmonic oscillator, right? Suppose you actually have something which has a friction force, right? Then there's an interesting question you can ask. For a given F naught, so suppose you're looking at a fixed frequency, right? I mean, fixed amplitude force you're putting on your spring mass problem. Or this could be a fixed voltage source that you're putting on an RLC circuit, okay? The question then is, what choice of gamma maximizes the steady state solution, if at all? So if you think about different choices of frequency for your force, like which one is coupling to the system most strongly? Which one puts energy in the best? Which one, and so we can study that question, right? What you got to do then is you got to solve the problem in general for arbitrary gamma. Then you calculate the amplitude of the solution. You differentiate that with respect to gamma, set that equal to 0. That should tell us what the maximum is, right? Because to find maximums, we look at critical points from calculus 1, right? That's the big picture of what I'm showing you here. So, so what you do is this is the again that thing we just actually worked this out, right? So here's the homogeneous solution. Oh man, I gotta get a new battery. Homogeneous. Come on, no, don't die on me now. Shake some ions loose. Let's see here. So that's the homogeneous solution. The point of this is just that we've done enough annihilating. We know what we have to worry about is that this has the same shape as a function as that, right? And it doesn't. These are linearly independent. This is a pure cosine. This is an exponential times sines and cosines. These do not overlap. What that means then is that the particular solution, it will suffice to look at a cosine gamma t plus b sine gamma t, right? So you plug it in, differentiate 2 times, plug it in, work it out, do the undetermined coefficients on this arbitrary problem. And what do you get? You get these 2 equations down here, all right? So I work it out. I find my A and my B are this. Pretty, huh? And then maybe I should have put this on your quiz. No? I mean, if I really put this on a test, I'd have to devote like a solid 40 minutes for this one. And it would not give me joy to grade this. But this is actually something you guys should be able to work out in principle. Anyway, so this is my particular solution for arbitrary gamma. The question is, what's the amplitude of this monstrosity? How do you calculate the amplitude of a cosine plus a sine like that? Well, the good news is that the amplitude of a1 cosine plus a2 sine, essentially in function space, these are perpendicular vectors. And so the length is actually the square root of the square root of the sums of the coefficients squared. This can be derived using trigonometry. The amplitude of the sum of the sinusoids is just the square root of the sums of the squares of the amplitudes of each piece. It's beautiful. And, or to quote my son Matthew, it's booful. And so that's quite awful. A1 is this. A2 is this times that. But you see what happens when you add them, you get this squared, right, plus that squared, which is exactly what we got down here. So it's really nice that you get basically one copy of this upstairs from adding the coefficients, and you get a squared copy of this downstairs from just squaring it, which leaves you a net of just one of these downstairs, which gives us this factor. So there you go. That's the amplitude for an arbitrary. That's the amplitude for the particular solution, the steady state solution for arbitrary gamma forcing function on the spring mass problem. Right. And then to find the resonant frequency, right? What do? We have to differentiate this with respect to gamma, set it equal to 0. That will tell us what the resonant frequency is. Okay? So I do that. I call this thing m. Why, I don't remember, but there it is. M is this thing, the coefficient. Ignore f, not just a constant. Who cares? Differentiate that. You get this. Of course, the denominator can't be 0, so we're just looking at the numerator being 0. The numerator can be 0, gives us this, which gives us that. Now, there are two cases. It could be that the 0 frequency is your best response. In other words, the DC solution, just the steady, just constant force gives you the maximum response. That's a possibility. And some problems are just like that. Like, you want the maximum coupling for a given F naught, you should just make it a constant force. That gives you the best. Right? That's a physical possibility. I have assigned homework problems in here in the past where I said find the resonant frequency, only to have them come back and tell me there was none. I mean, what they really mean is 0 is the resonant frequency. But I was like, oh man, didn't know that could happen. I should have trusted the math, though. It's right there. DC, I mean, the 0 oscillation is one possibility for the max response. But the other case would be when this thing is 0, which it's a quadratic in gamma, right? So we can solve, and we get plus or minus that, which cleans up to this. So this is the critical frequency, square root of k over m minus b squared over 2m squared. This is not what? You might, by intuition, have expected this would be what? This, right? Is it that, though? No, I don't think so, because there's a 2 here. That's not 2. I'm pretty careful with parentheses, guys, right? If I could get you guys to be careful with parentheses, it would be amazing. But I've given up. So, like, you guys have decided, I think you have a theory of life or something like this. You have this theory that you have so much to write in your lifetime. And so you're worried if you write too much, you'll die. So you're being careful to only write what's needed and no more. Something like that. Although sometimes you write a bunch of irrelevant algebra, so that doesn't really work. My theory doesn't work. But there's this great book by a famous Japanese mathematician. It's very popular, and it's called Galois' Dream. It has literally nothing to do with Galois theory, which is interesting. But this book, one thing that's so fun, it was written by a Japanese professor in the 60s. And so it has lots of things about marriage and like relationships, which seems wholly inappropriate for a math book. And there's like a disclaimer at the start of the book that says something along the lines of, this was written for a different culture and a different time. Please do not be offended by the professor's comments or something like this. He actually respects women, blah, blah, blah. It's like, what? Anyway, so you have to look at this book. It's fun. But one of the things in this book is he tells a story about how as a child he imagined he had a tail. And as he walked, his tail dragged behind him. And when his tail was fully extended, then he would die. So he used to spend his childhood trying to learn how to walk null homotopy paths as he walked a path, which is just a fancy way of saying he tried to not walk around things so his tail would get snagged and then pull out. So and then he would get very annoyed when people crossed his path behind him, because that would, this is for that's what made me think of your writing. That was the point. Anyway, so not the same as the quasi-frequency, the natural quasi-frequency for the system. I mean, I think that's a little bit surprising to me. However, in the case that in the case that beta is equal to 0, right? The quasi-frequency and this resonant frequency, although this derivation breaks down, right? Technically, I shouldn't be allowed to put beta equal to 0 here because beta equal to 0 doesn't, our particular solution doesn't allow for that, does it? Like we assumed that beta was non-zero in our derivation here, yet if you take the limit as beta goes to 0, you get back to the critical frequency being the resonant, the simple harmonic motion frequency, as does the natural quasi-frequency. Sorry, shut up. Now here, I derive the same thing for an RLC circuit, all right? But I do it a rather different way. Instead of using real notation, I say, you know what? If I'm going to solve cosine gamma t, if I want to solve for a particular, external voltage of cosine gamma t, I might as well solve the corresponding complex problem, which would be v naught e to the I gamma t. See, e to the I gamma t is easy to solve because the particular solution just has the form a e to the I gamma t, right? So you can differentiate that once or two times, no problem, and plug it in. You get this, and then I can solve for a. And so in the complex notation, it is way, way easier to work out. Well, I say it's way easier. You can disagree if you like, but this is the particular solution, and here I've went to the, I mean, if you don't care about the real and imaginary parts, it's even easier because you could just kind of like go, okay, well that's a. But, you know, I make it real. So here is this times cosine plus that times sine would be the real part of QP, which then would be the solution which gave you back the cosine, because cosine is the real part of the forcing term. So if there's a different way to derive, I mean, I guess we could, here, let's try this out and put this away. Oh, no. I'm sorry, guys. Sometimes I'll spend like a solid half hour of class deriving the critical frequency. It just didn't happen for us this semester because I gave you guys extra time on your quiz. I hope you can forgive me. I mean, it's what? You'll forgive me? Okay, good. Here, let's try out this complex scheme for a second here. Suppose I want to solve y prime prime plus 4y equal to, gee, I don't know, cosine of 3t. So the idea is to say, aha, cosine of 3t is actually the real part of e to the 3it. Because e to the 3it is cosine 3t plus I sine 3t, right? So I complexify the problem. I basically say, okay, so z prime prime plus 4z equals to e to the 3it should tell me something about my original problem. This is easy to solve because I just say, okay, so zp is a e to the 3it, which tells me that zp prime is 3ia e to the 3it, and zp prime prime is minus 9a e to the 3it. Plug it in. You've got minus 9a e to the 3it plus 4a e to the 3it equals e to the 3it, and that tells us what? Minus 5a equals to 1, therefore a is minus 1/5. And so we get z is equal to minus 1/5, I mean zp is minus 1/5 e to the 3it, right, which is minus 1/5 cosine 3t minus I over 5 sine 3t. But because this is a linear differential equation, right, this has real and imaginary parts which solve corresponding up here. So what I'm trying to say is Theory I haven't entirely explained yet, but sorry about that. From this, I can see that this will be the particular solution to my initial problem. So basically, uncomplexifying, it tells me that yp equals to minus 1/5 cosine 3t solves my original problem, the particular solution for my original problem. And by the way, if I had been solving y prime prime plus 4y equal to the sine of 3t, then this would have particular solution minus 1/5 sine 3t just the same. Yeah. What if I had like y prime prime plus 4y equal to 7 cosine 3t minus 5 sine 3t? So I do 7 times that one. Did I have a minus? Oh yeah, I have minus in both of them, do I? Minus 1/5 cosine 3t, and then minus 5 times minus 1/5 sine 3t. I'm using what's called the principle of superposition, which I have somehow failed to talk to you about again today. So next time. Sorry, guys. So next time, hopefully superposition, and I'll talk to you about the Cauchy-Euler problem, most likely.